Okay, we have spent several videos now dealing with this integral, and there's nothing really complicated about the integral. What we have done is to solve it using different types of substitutions. In the very first integral, we solved it quite easily using this substitution. We obtained this expression, and then we took the differential of this expression, and we obtained this, proving that it was correct. And then we proceeded after that in a different video to solve it with this. And actually this was equal to, u was equal to a times the hyperbolic sine of x. And when we made that substitution, we got this expression, which was different than this one. So we spent the whole video taking the differential of this expression here, and indeed we obtained what was under the integral sign, proving that this also is a correct answer for that integral. And yet there's a third way that we can do it. Here we have a constant squared plus a variable squared. And with this hyperbolic identity, there's yet another identity that fits that general pattern. We have a constant plus a variable squared. So in theory, we should be able to solve this integral based upon this identity, a substitution using it. And let's see what happens. If we solve it, will it be one of these, or will it give us yet another expression for this integral? So, like before, we start off by saying, let u be equal to a times the hyperbolic cosecant of x. If we do that, the denominator here is going to be a squared plus a squared times the hyperbolic cosecant squared of x. And if we factor the a squared out, that becomes 1 plus the hyperbolic cosecant squared of x, which is the hyperbolic cotangent squared of x. So this part of the integral is now a squared times this, and now we have to find out what du is. So du, and hopefully you remember your basic hyperbolic derivatives. This is going to be minus a times the hyperbolic cosecant of x times the hyperbolic cotangent of x dx. So this integral here now becomes the integral of, here's du minus a hyperbolic cosecant of x times the hyperbolic cotangent of x dx divided by this, take the a to the outside, a squared, and we have the hyperbolic cotangent squared of x. So let's see what this leaves us with. We're going to have this will equal minus 1 over a, the integral of, these will cancel away, and I'm going to have the hyperbolic cosecant of x divided by hyperbolic cotangent of x dx. Now let's see here. This, I'm tempted to say, this would be 1 over the hyperbolic sign. This would be the times hyperbolic sign over the hyperbolic cosine. So let's see. Let's write it out. We'll have, this should equal minus 1 over a. The integral, this is 1 over the hyperbolic sine of x. And this is the hyperbolic cosine of x divided by the hyperbolic sine of x. And we're going to multiply by the reciprocal of that. So this will end up being like this. dx. This is the reciprocal of this, taking it to the denominator, taking it from the denominator up to the numerator and multiplying. So this and this go away, and this equals minus 1 over a, the integral of 1 over the hyperbolic cosine. That is the hyperbolic secant of x dx. And hopefully you remember from before, this will equal minus 1 over a, inverse sine of the hyperbolic tangent of x. Okay, let's see here. Our original integral, of course, is not in terms of x, it's in terms of u, the variable u. So we go back here now to this, and we can determine that the hyperbolic cosecant of x equals u divided by a. But we need to find out what is it for the hyperbolic tangent of x. If we know it for the hyperbolic cosecant of x, then we should be able to determine it for the hyperbolic cotangent of x, take the reciprocal of that, and then we should have it for the hyperbolic tangent of x. So let's see here. The hyperbolic cotangent of x, that will equal the square root of 1 plus the hyperbolic cosecant squared of x, or 1 plus u squared over a squared. And this, if we do the algebra here, this should be equal to the square root of a squared plus u squared divided by a. That's the hyperbolic cotangent of x. We want it for the hyperbolic tangent of x. So we can say that will equal a divided by the square root of a squared plus u squared. So our answer here now becomes minus 1 over a times the inverse sine of the hyperbolic tangent of x, which is this. So I'm going to have a divided by the square root of a squared plus u squared. And this plus a constant that should be the solution for this integral. Let's just erase some things here and make some space. Let's take this and write it upstairs. So let's see, we are going to have minus 1 over a inverse sine of a divided by the square root of a squared plus u squared. There it is. And that is not the same as this one. So it looks like we have yet a third expression for this integral. So let's be diligent, and we can take the differential of this side of the equation and see if it gives us this. And if that's true, then we'll have shown that this equation here, with the three types of substitutions that we could use to solve it, each of them yielded a different type of answer. But each answer should be correct. We know these are. Let's take the differential of this and see if it gives us this. We're not going to have enough time to do that in this video. Join us in the next video. Let's do that and see if we can get this wrapped up.